All right. So after doing some calculations, I want you to take a step back, monologue for a little bit, big picture perspective of physics. Okay. So, I don't know if you like dawned on you as you're doing the calculations, but you're like, huh, the process for doing this seemed pretty similar to the process mathematically in the calculator that I was doing this. Okay. Turns out that gravitational force and electrical force are two of the four fundamental forces of our universe. Okay. It's pretty crazy the fact that two of the four are like spitting image of each other, like in terms of like the math. And they're like, well, it just happens. Well, turns out that if this was slightly different, life as we know it would not exist. If this was r to the first instead of r squared, electrons would be like flying off, wouldn't be held together. Molecules wouldn't exist, like atoms wouldn't exist. Molecules is just like, okay. If this was r to the 2.1 power, life wouldn't exist. Electrons would be, and like things couldn't bond. Like it just would not work. Like this needs to be just so for chemistry to work. Okay. And there's some other details of this for forming molecules and atoms that have to be just so or life doesn't exist. Like the mass, so electrons are very, like, the percentage of mass that electrons have in the atom is super tiny compared to protons. If this wasn't so, things, molecules wouldn't work. And like also the mass of protons versus neutrons, we kind of talked about this a little bit with the Big Bang, but neutrons are a little bit more massive than protons. If that didn't happen, fusion wouldn't happen in stars, producing elements and life. Okay? So it's like, it's super crazy cool as we study stuff. Like, whoa, man, I'm glad I'm alive. There's a lot of things like super fragile to make it possible for us to be here. Um, so there are four fundamental forces: gravity, electrical force, strong and weak. Um, Gravity, we've studied. Electrical force, we're starting to study. Strong force. So where do protons exist? In the nucleus, right alongside of neutrons and other protons. Protons are what charge? Right next to other positive. Does anybody see like the conundrum there? Like protons are just like packed in there with other positively charged protons. Think they like that? What keeps them together? The neutrons. The neutrons, they're like Switzerland. Like, come on, guys, can't we just get together? Like, just coexist. Like, come on, it'd be good. No, neutrons don't do a thing. Okay. Turns out there's another force at play at really small distances called the strong force, stronger than the electrical force of repulsion. We got really creative with our names. Okay, strong force. So this happens only at really small distances, like the radii of an atom, of a nucleus of an atom distances. But there's there's a lot of potential energy associated with that force, and that's where we get atomic bombs from. We take the nucleus of really heavier elements and we break them apart, and we're like releasing the energy stored in the strong force, and that's where atomic bombs come from. Okay. The fourth one is weak force, and that's also at the subatomic level, and it's weaker than the strong force. Weak force. Why not? So those are the four that we know. Now, check this out. Last semester, we were doing free body diagrams, and we'd say, okay, there's like 5, 6 forces. Gravity, gravitational force, we're down with that. But then we had like applied force, normal force, friction, tension, there's whatever. Those other forces at a molecular, like microscopic level, can be boiled down to the electrical force of attraction or repulsion. When you touch something at a microscopic level, that's really the molecules of your finger are repelling the molecules of the desk. Kind of like two magnets going boom, boom, boom. So like this whole like irritating your siblings, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you. You'll get in trouble. But does that make sense? At a microscopic level, they're just things being repelled, and that's touching, that's triggering nerve endings to say, oh, that's touching. Okay, how are you able to hold something? Well, I can hold that like that because I've got enough of these things spread out over here that it's just repelling upward. Does that make sense? People are like, how do you get stabbed? Like, well, the molecules of your knife are like stronger enough to like repel the skin molecules, and like it's just like pushing things away. Does that make sense? It's not like we're not cutting molecules. It's just like, yeah, that makes sense. It's like going through, sticking your finger through Orbeez. That would be fun. Yes. Everybody feel. All right. That's my monologue. Just want you to appreciate the life around you. Like, yeah. Tell your neighbor.
No, it's the force that originally was there is triple.
Here's the equation. Correct answer is?
C.
I got 1 vote for C.
B.
I got some votes for D's and some votes for B's.
No, don't do me wrong.
All right. So we'll say Q2 is 3, and then it changes to 6. We doubled this.
Wait. Oh, I'm thinking of the wrong object.
Okay. We went from 3 to 6, so we doubled that, so that doubles this, and it's going in the opposite direction because we're changing the sign.
I didn't read the question properly.
B.
I thought we were replacing the score.
Good with that?
Yeah, that would be 1.5. Yeah.
Tell your neighbor.
I think it's E. Why D? Nah.
Correct answer is?
E.
Electric eels. Okay. We're doubling that. No, we're quadrupling that. So you need to square the 4. Comes 16 on the bottom. Good? Thumbs up when you have a guess. Have a conversation.
It's 4, but it's also square.
2r squared 4. Yeah.
This distance is double, but small, so the sign is bigger by like feet, so it's so I think it's C.
Well, you'd be wrong. You want to put one on it, bro?
It'd be the same.
Well, not gambling. I mean, it's not gambling if you know
Correct answer is? All right. So this one's K, capital Q, lowercase q over R squared. Okay. We're just going to say that has a coefficient of 1. K, capital Q, two Q over 2R squared. That becomes 2 over 4, so 1/2 coefficient. Okay. Here we have K, Q, 4Q over 2R squared. You get 4 on top, 4 on bottom, 1. Dangerous dinosaurs. Good with that? Okay. Here's how lightning works. In a thunderstorm, there's a lot of turbulence. Electrons are smashing into, or sorry, molecules are smashing into each other, ripping electrons off. So we're like charging by friction. For reasons that we're not sure why, we just know this happens. The majority of the time, it's not always, but the majority of the time, the electrons go near the bottom side of the cloud. Positively charged things stay on top. Okay. Because of this collection of negatively charged particles on the bottom side of the cloud, that chases away electrons in the ground. Are we good so far? Okay. These electrons in the cloud don't like their scenario. They're like, it's so crowded, gotta get out. And so they're like, we should send scouts to find better lands. And so they send out these step leaders, which are just electrons trying to like find their way, as like stacks of electrons trying to find their way to better environment. As that happens, electrons in the ground are running away even more, making the ground more positively charged. So in response to that, air molecules around the ground are neutral, become polarized, and are attracted to the positive ground. Trees, grass, whatever is on there. And so they get attracted, and then when they touch that, they deposit some of their electrons, because electrons are like, I want to go to a better environment. And so it makes the gas molecules in the air positively charged. We good with that? Okay. Now, I know that I've preached to you time and time again that protons don't move. That is true for a solid, because the protons are in the nucleus is trapped in the crystal lattice that can't move. In a liquid and a gas, the molecules themselves can move. So the positively charged molecules can also move. Does that make sense? And so you get a collection of these things, and they start forming positive, called streamers. These step leaders and streamers happen really quick, and typically you won't see them. Okay, it usually takes a camera to see the low intensities of light here. Okay, I've got a film that would show this. But when one of those step leaders and streamers connect, that's where lightning starts. Okay, so it's like a stoplight turning green. The cars stacked up nearest the stoplight go first, so and then the ones towards the end then can go. So these rushing electrons are what form lightning. Okay, so the electrons are going from the cloud down, but the light that we see are from these rushing electrons hitting air molecules around, causing the, okay, so chemistry review, where light comes from. When an atom gets excited, it sends an electron to an outer orbital, and then when it falls back down, it emits a photon light. Yes, no? Is that in there? Okay, ready? Light's produced. Electron gets excited, goes up to a higher orbital state. When it falls back down, it emits a photon. Okay, and that's happening here where the cars are rushing first. So it looks like the light goes from the ground up, but really the stuff's going from the cloud down. Electrons are going from the cloud down. Okay. I've got a video here that tells the exact same thing I just said. It just does it in animation form.
It's a small pump inside the cloud 5 miles up. A spurt of electrons rushes outward, travels 100 meters, then stops and cools for a few millionths of a second. Then the stream lurches off in a different direction, cools again and again. Often the stream branches and splits. This is not a lightning bolt yet. It's called a stepped leader, an intensely charged channel leaping and branching down. As it gets close, its electric field begins to exert a pull on the ground.
When that step leader is within 10 or 100 meters of the ground is now aware of there being a big surplus of negative electricity, which has come down on a conductor. Certain objects on the Earth respond by launching little streamers up toward the step leader. Weakly luminous plasma filaments, which are trying to connect with what's coming down. If you happen to be standing there, maybe a streamer is going to leave your head and head toward that step leader. A telephone pole might launch a positive streamer. A blade of grass might launch a positive streamer up toward the step leader. It's that special one which makes the connection, which gives rise to the return stroke, and then this catastrophic 10,000 ampere current flows. That closes the switch.
When that connection is made, the electrons drain to Earth in a blinding bolt of light. The part of the channel nearest the ground will drain first, then successively higher parts, and finally the charge from the cloud itself. So the visible lightning bolt moves up from ground to cloud as the massive electric currents flow down.
Okay.
So
here's a step leader. We don't see this happen. This is slow motion and low intensity light, but we see the lightning bolt. Good with that?
That's really cool.
It is super cool.
Let me see like a few more times.
One more.
It's like sometimes you see a light hit like this. Like it's like spread out. I mean, like it hit.
Could have. Okay, so these are pictures of positive streamers.
Give that big anvil strike last night. We've got it. We've got it.
Okay, notice how which way the light's going. The light's going from the ground up versus electrons go from the cloud down. Okay?
What makes the noise?
Great question. So the thunder comes from making the air super hot where the lightning is. It expands and creates this vacuum. And then when it cools down, it's like all the atmospheric pressure pushes everything together, and that when they crash together, that's thunder. Very cool. So, got a pre-quiz due tomorrow.